Everyone, and welcome to today's webinar organized by Manav, the Human Atlas Initiative. My name is Chhavi, and I will start with an announcement. If you all have any questions during this talk, please write them in the Q&A tab below. So, to start, on behalf of the Manav team, I welcome our today's speaker, Dr. Pranay Goel. He is joining us today from the Indian Institute of Science, Education and Research in Pune. Dr. Pranay is an expert in data science, and his team at IISER uses mathematical modeling to understand biological processes involved in various diseases. The interdisciplinary nature of his work, that is combining math, data science, and biology, is particularly fascinating for me. Today, Dr. Pranay will walk us through how scientists use mathematical concepts to understand and model the intensity of an outbreak such as COVID-19. So welcome, Dr. Pranay, and over to you.
Thank you, Chhavi, and it's a pleasure to be online and be giving this talk. I'm going to turn over to my slides, and hopefully you'll be able to see them. Can you see my slide?
Yes.
Okay, wonderful. Okay, great. So what I thought I would do in about the next 30 minutes or so that I have of this is to give you a sense of what this very famous constant R0 has become. So we are all very interested, and we've been hearing a lot about this constant R0, the basic reproductive number, so to speak. And there's a lot of interest in asking, what is this number? How is this number calculated? What does it tell us to compute this number? So on and so forth. The R0 is essentially a number that tells us whether there's going to be a pandemic, whether an outbreak is going to turn into a pandemic, or if an outbreak is going to die away. So I'm going to show you features of R0 and what R0 stands for, what it can be used for in quantifying an outbreak, the intensity, the peak, when is that peak reached, and so on and so forth. And all of those will have, R0 will have a bearing on all of those questions. Now, I want to start with a disclaimer that this is a very academic talk, a very textbook talk. So it's essentially a beginner's guide to understanding the literature that's in this subject, and some of the scientific discourse that one hears a lot about, either on the news channels or if you hear some scientists discussing it. Epidemiology is a very involved science, and I am not professing by any means to give you a cookbook for doing epidemiology. That's best left to the professionals. So what can we do? What we can do is to try and understand some of that discourse, and we want to develop methods that are simple enough that you can run models on your laptop and then try and get a sense of what it is that these scientists are talking about, right? So there is, for example, a good amount of controversy regarding the lockdown, and there are countries that have used a very strict measure of lockdown, such as India. India is one of the strictest lockdowns in the country in the world. And there are countries that have had a very mild form of lockdown, which is largely physical distancing, such as, for example, Sweden. So the point of this is to say that there are differences in the approaches people take to managing an outbreak, managing a pandemic. And R0, in fact, actually has a bearing on all of these questions. So what I'd like to show you, what I'm going to show you, is to give you essentially a tool, a simulation package, and I will write down some scripts to give you a sense, and I will run those simulations for you, to give you a sense of what you can expect to do with these models. Now, these models in their full-blown sense they're extremely sophisticated, but many of the features that that are talked about can be understood through very simple models. So that's my goal over here. to give you an empowering technology, a very basic sense of the kinds of models that we provide in these, and give you a facility to run some of these models on your own. And you can vary parameters, and you will be able to see for yourself how that influences the outcome. In a second part of the webinar, we will actually look at some data from the number of cases that have been reported in the worldwide with regard to COVID-19, and we will discuss some of the ways in which one uses that data to compute this R0. But in this first part, we will talk more about what this R0 is and how does the R0 help us quantify the intensity of an outbreak. Okay, so with that introduction, let me start a little bit into describing what the basic reproduction number is in a very general setting, in a very general sense. So the R0 is essentially a measure of how many people on average does an infected person that's introduced into a susceptible pool of persons, how many people in turn, how many secondary infections did this person lead to. For example, if there is a person introduced into an eye population, that means the person who is infected enters into a population, that population, consider COVID, for example. Now, at the beginning, none of us are immune in the sense that our bodies have never seen coronavirus before. So we don't have any immune response in the sense that our bodies don't get antibodies. It's novel with respect to that. So this person is going to infect other people. And on average, how many people does this person infect is the question that one would like to have, or one would like to ask. Why? Why would you want to ask this question? Well, it's quite straightforward. If a person infects one other person, and let's say there are 5 individuals who are introduced at some time into a population. When I say somebody is introduced into a population, I don't mean in the sense that a person carrying the virus has been placed there. I just mean it in the sense that that person carrying a virus has entered into a population. So an infected person, if there are 5 such individuals and they each infect one, then at the end of the day, you'll have 10 infected individuals, 5 of whom will presumably recover, and there'll be 5 more people who will be infected. And so they will just march along, and the infection will stay at the level of approximately between 5 and 10 people throughout. But on the other hand, if one person infects 2 people, well, then 2 will infect 4, and 4 will infect 8, and 8 will infect 16, and the whole thing just blows up very quickly. It becomes a geometric progression. The process grows geometrically, exponentially, if you like, to think of. And then suddenly there's going to be an explosion of people who are infected, right? Just because the whole thing is growing geometrically. So what is the outcome? Where do you think all of this goes? Well, if there was an infinite population, then this number would just start going up, right? But at some point, a very interesting thing happens, and that is that when there's sufficiently large numbers of people who are infected, well, now the virus finds it more and more difficult to find a person who has not previously been infected. So those people who have not previously been infected, we'll call them the susceptible people. So if the virus finds very difficult to find susceptibles left anymore, because it sees a whole crowd of essentially infected people all around it. This is when sufficient infection has spread into the population. And at that point, the virus is going to slow down. The rate of spreading is going to slow down. And eventually, as it finds lesser and fewer people, eventually the infection goes away, right? So that's the general intuition behind all of this, behind how an epidemic spreads. The number of infections rises, and at some point it becomes limiting in its own sense because it does not find other susceptible people, and then it starts decaying, and at some point it is gone. It becomes extremely low in the population, right? So we want to understand this dynamics, and we'd like to build some model to try and show whether this behavior can be expressed in those equations, right? Now, what was the crucial step in knowing this, in knowing whether an infection will spread in a population, whether it will grow in a population? The crucial step is to ask whether this basic reproduction number, R0, whether it is greater than 1 or not. If actually the R0 is less than 1, that means one person is going to infect fewer than one person. That means if there were 10 people, they're going to infect in turn fewer than 10 people. Well, then eventually and very quickly, the infection will actually disappear in the population. It will not grow. So to ask ourselves whether this is going to be, whether an infection introduced into the population will actually become a pandemic, you have to ask the question whether R0 is greater than or less than 1. So this R0 equal to 1 is a threshold. It's the critical number that decides, that determines for us whether something will spread as a pandemic in the population or not. So one asks the question, well, what is this R0 determined by, right? And how does one calculate it? If someone really wanted to estimate it, it's a number, and we'd like to be able to estimate it to know whether it's 1.5 or is it 0.7. It makes a big difference if it's 0.7 versus 1.5, because at 1.5, if the R0 is 1.5, it will grow, as we said, and if it's less than 1, then it's going to disappear. How does one calculate it? Imagine that you could know at the beginning of the spread of right at the very start of the epidemic spread, imagine that you could know all of the people who were infected. Let's say there are a couple of people if they're infected, and we know all of these people, who they are. Then as they spread through the population, you can do contact tracing. You can ask, who are these people, who have these people come in contact with? You test those people whom this person infected has come in contact with. This person infected will have come in contact with many people, but on average, a few of those people that have been come in contact with this person, with the infected person, will have been infected. So you can ask the question by simply following the data, the evidence, how many on average will an infected person transmit to? And that will give you an estimate of R0. And if you do this in an average sense, over a period of time across many individuals, you will get an average number R0. So SARS-CoV-2 has an R0 of approximately 2. It's been reported to have a number anywhere between 1.5 and say 2.5. So on average, a person with COVID is going to likely to infect 2 other persons. So there's a secondary infection to 2 other people. Okay, so well, that's great to know that there is a number that which can quantify the extent of an epidemic. What are some of the things that R0 can be used to tell us? Well, first, it can tell us whether it's a pandemic, whether this disease is a pandemic or is going to be a pandemic or not. So that means you can know it early enough during the spread of the pandemic, whether this is going to be a pandemic, depending on the R0. But the R0 also tells you when the peak of the infection will come, what will be the size of the peak, and so on and so forth. So I'm going to show you all of those in simulations to follow. So let's take a quick look at some of the R0 numbers of several pandemics that have spread in the past, and you can see that COVID-19 has been reported. There's a very wide range of R0s that have been reported in various studies, and we can certainly discuss why there's such a wide range has been seen in different studies. But on the whole, you see something as low as 1.4 and something as high as 5.7. But a lot of studies have reported it around between 1.5 and say 2.5. So I would take an average number of a representative number of about 2, although it makes a big difference whether it's 1.8 or 2.2. You will see in a minute in the simulations that this will make a difference. Measles, for example, has an R0 of very high R0 of about 12. That's really high. HIV has an R0 of about 4 typically. Common cold has an R0 that is somewhat higher than COVID-19, 2 to 3, if COVID-19 has an R0 of 2. So R0s of different diseases are different. What are some of the influences? What are some of the things that can influence an R0? Now I will talk about, when we talk about R0 as this basic reproductive number that says how many secondary infections is one infected person likely to cause. That's one way of looking at it. Another way of looking at it is in the threshold sense that I said. Well, when you calculate R0 from models, which we'll do in a minute, then R0 is thought of as a threshold number, and what you really care about is whether or not R0 is greater than 1. And we will use the equations to show that this number actually appears in the equations, and the quantity R0 greater than or less than 1 is going to determine whether the rate of infections is going to be positive, in which case the infections will grow, or whether the rate of infections is going to be negative, in which the infections over time will decrease, will go down. Right? So before we do that, in the next slide, I want to put out a couple of features of R0 that one should keep in mind. R0 itself cannot be changed. It is the rate of infections when there are no interventions, right? So you'll see in a minute that R0 is a number, right? And you really can't change R0. Although you will see on, in the debates on TV and so on, you will see that people will say that, R0, we'll try to bring down the R0 and so on and so forth. So what exactly does that mean? What that means is they're talking about an effective reproduction number, R effective, and that is something that can be changed. And we'll see in a minute why people claim that R0, or which is essentially what they mean when they mean R effective when they're saying R0. Okay, that's essentially what I'm trying to say. So for example, physical distancing will reduce the rate, the contact rate between people. So if you imagine that you're completely isolated from someone and you're infected, then it's very unlikely that you'll transmit it to somebody else. And so in fact, if you're isolated, then your R0, and if everyone was isolated who is infected, then R0 will essentially be 0, because you cannot transmit to anybody else, right? And that's not reality. That's the reality is going to be somewhere different from that, and we'll see in a minute. But it does make the point that in a theoretical sense, things like physical distancing can reduce R0, and that it is essentially lowering R effective, and we will use that interchangeably with R0, and the interpretation will be based on the context in which it is used. Okay. So I'm going to talk about what is called the SIR model. This was introduced by W.O. Kermack and A.G. McKendrick in 1927. So it's been around for a while, almost 100 years now. And what it talks about is to consider 3 kinds of people in a population. Those that are susceptible. In fact, for COVID, SARS-2, for coronavirus, we are all susceptible to begin with, because this is the first time humans have actually seen this coronavirus in the population. So everyone is susceptible, though to different degrees. And we'll come back to that subtlety in a little bit. But once you are susceptible, and we'll call that the S group, the susceptible group, then those people will get infected at a certain rate determined by R0 essentially. So there's a certain rate at which susceptible people get infected, and they move into the pool of infected people. And we'll call this the I pool, or the infected pool. And eventually, as the disease, as people recover from disease, they will move into the recovered pool. After they've become infected, they will move into the recovered pool. And at that point, they're either immune, or a small fraction will unfortunately be will be dead. So the R pool is going to include not only people who have recovered, but sometimes it's also includes the people that have been removed from the population entirely. So the R pool is going to be people who have passed through the infection onto the next stage. And typically, a large fraction of the people in SARS-2 will be the recovered pool. So these are the equations over here. I hope you can see my cursor. So there's ds by dt. These are mass action reactions. Just like you would write down the law of mass action for a chemical reaction, you can actually write down a similar mass action law when you consider the fraction of populations in the S pool, the fraction of people in the I pool, and the fraction of people in the R pool. So let's quickly go over this. Well, ds by dt, now S here actually stands for the number of people, not the fraction of people. You can write all of these equations as fractional quantities by taking, say, small s equal to big S by n, which is the fraction of susceptible individuals divided by the total population size n, right? And now, so ds by dt is going to be, so the susceptible pool will move into the infectious pool at a certain rate beta. Okay? This is effectively the rate at which the susceptible pool gets converted in infection pool. So this is the flux from the susceptible to the infectious, and it's going to depend not only a certain rate beta, the transmittivity, how people become infectious, but it's going to depend on the size of the infected pool, and it's going to depend on the size of the susceptible pool. The reason it depends on the size of the susceptible pool is because you need susceptible people to get infected. And the reason it depends through a product on the infected pool is because you need people infecting other people to spread the infection. So you need a product I times S, which will actually move the flux of people from the susceptible to the infectious. And the infected people flux will be the flux that comes from the infected people, and minus the flux that corresponds to the infectious people recovering. So the rate of recovery, if you assume that that is gamma, then di by dt will be beta times I times S over n. That's the rate at which the susceptible people become infectious, minus the rate of recovery times the number of infected people. So minus gamma I. The rate of recovery is simply gamma I. Now there's a simple conservation law here, and that is because we assume that this population is sort of closed. It's also homogeneous. Those are the assumptions that go into the SIR model. And if you assume that the entire population is closed, that means there are no births and deaths occurring. This is happening very quickly, so we don't consider births and deaths. That's happening on a longer time scale. So on this time scale, on the epidemic time scale, S plus I plus R will be the constant of the size of the population N, right? So in other words, you're either S or I or S or I or R. And so therefore the sum of all of these, the total number of S and I and R, will be the size of the population N, right? Having an equation like this actually allows you to drop the R equation entirely, because you've got one constraint. It was a system of three differential equations with one constraint, so it's effectively a two-dimensional system. So we will retain S and I, the equations for S and I. Okay. So the basic reproduction number now, in terms of the model, is going to be beta divided by gamma. Remember that beta is the rate at which, think of it as the reciprocal of the typical contact time. How long does it take for for an infected person to make contact with another person and turn them infected? So that's 1 over tau c, 1 over tc, and that is your beta. That's your rate at which you are going to infect others. And the typical recovery time, let's say, how long do you stay ill before you recover? Well, let's assume that it takes about a few days. So for SARS, it will take a time of about 10 days to recover. So then 1 over TR will be the gamma. It's the rate at which your people are recovering, right? So the basic reproduction number in this setting is beta over gamma. It's the rate at which people get infected divided by the rate at which people recover, right? So this is, so why would you want to consider this? You can want to consider this because look at the next equation. The rate at which the number of infected people, that pool of infected people I goes up, is actually simply restating this equation. That's going to be R0 times S by N. S by N is the number of susceptible. So S by N is the fraction of susceptible people. So it's R0 times the fraction of susceptible peoples at that moment in the population minus 1 times gamma times I. So if this gamma is a positive number, so if this quantity is positive, then di by dt will actually be positive. And if this quantity is negative, then this di by dt is going to be negative. And that's the key equation that helps us understand whether the infections will grow over a period of time, or whether the number of infections will actually decline over a period of time, but depending on whether this is positive or negative, this bracket over here. And essentially, right at the beginning of of the epidemic, S is pretty much N, right? Everyone is susceptible. So this fraction is essentially 1. So right at the beginning of the epidemic, you get to compare R0 to 1. If R0 is greater than 1, then this quantity is positive and the infection will grow. If R0 is less than 1, then this quantity is going to be negative and the infection will decay, right? So the critical quantity is whether or not R0 is greater than 1. And this equation actually holds at all time, but right in the very early stages when S hasn't changed, the number of susceptible people is very, very large, this fraction is almost 1. And therefore, you get to compare R0 to 1. And that's the key insight for discussing these things. So I'm going to rapidly run through some simulations. But before I do, what are some measures of reducing R0? In what way can you actually hope to reduce R0? Well, what you're reducing is not R0. What you're reducing is beta. It's the rate of infectivity. It's the transmission rate that you would try to reduce. And so you can imagine that physical distancing might help reduce transmissivity, washing hands because you're slowing down the virus. When you're killing the virus, washing hands, avoiding large gatherings so that so that spreaders are fewer and there's a lower probability of contact and so on. Transport networks have some effect. They usually slow down the network somewhat. And then there's lockdown. And there's various kinds of lockdowns from very severe in India to mild considerations in Sweden. You have to note that these measures have to be tailored to the nature of the disease as well. So for example, you might ask yourself the question, how effective is school closure if the children are at low risk of falling ill from infection? In other words, would you not rather try to protect the elderly? You might exercise a greater deal of caution over the elderly and those who are immune compromised in order to be able to effectively reduce the rate of transmission in the susceptible population, in the truly susceptible population. Okay, so let's take a quick look at some of the simulations here. So I am going to show you I'm going to switch to a little script. Oops. Sorry, I need to view share. And so I hope you can see a little bit of a script that I've written. And this is a very straightforward script. And I'm writing it for this program called XPPAUD, XPPAUD. And you can see that S prime is minus beta times S times I divided by N. I prime, which is the I pi dt, is beta times S times I by N minus gamma I. And I've listed out a bunch of parameters. The size of my population, N, is 1,000. I'm taking a relatively small population. Let's say a community of 1,000 people. I'm also going to initialize S to be nearly all of the population and one infected individual at the beginning. So let's take a quick look at what the simulation would look like. And I'm going to switch sharing to simulation. All right, so this is the XPP window. And what essentially I've done is I've used this program XPP to run that script that I just showed. And I'm going to run it right now for you. Initial conditions, go. So this curve, and all of the details of how to run these simulations are there on the website that we shared with you. It's a program written by Bard Ermentrout. It's a free piece of software, very light footprint, and it makes it a charm to use differential equations, and it's really, really straightforward to use, as I've just shown you. So if I integrate those equations that I've just shown you, the total the total susceptible pool has gone down to about like so. Now I'm going to add a curve that corresponds to the infected individuals, and there you go. There you see it. So the infected individuals will rise in the beginning. It reaches a maximum peak, and it comes back down, right? So those are the infected people. That's what it looks like. I'm going to also add the recovered pool on top of this, and there it is. So the number of recovered people is actually going up like so. You will notice that after the infection has passed through the population, there is still a substantial number of people that are left over who are still susceptible even after the infection has gone through the population. Even after the infection has nearly finished, there's still going to be a pool of people that are going to continue to be susceptible, right? And in this model, R will be 1 minus the number of people that are left over. Okay. All right. So you will see the R0 can be used to also calculate the peak of the infection. The peak of the infection is N over R0, right? It can be shown. And so when about half the population, say this is the peak, right? So when about half the population has been infected, when S rather falls below R0 by N by R0, that's when the peak of the infection is reached. Right. So there's a couple of things. I'm running out of time. Chhavi, should I continue to with my slides, or should I wrap up and let people take questions?
No,
I can finish up in 1 or 2 slides if you like.
Yeah, please
Sorry?
continue, Dr. Pranay.
Okay, sounds good. So let me talk a little bit about this notion of herd immunity. Now, let's go back a little. Okay. So the effective reproduction number is basically the number of people that are susceptible at any given time times R0, right? So that is the effective reproduction number at any given time. What happens when a sufficiently large number of the population has been infected? So the number of susceptible people actually goes down. When the number of susceptible people actually goes down, you will be able to, the virus is going to find, the infection is going to find fewer and fewer people to infect, at which point it starts to turn around. That means it cannot continue to grow up. It actually starts to turn around, it levels off, and then it actually goes down, right? So let's show some slides which can clarify this notion. I'm going to try and switch slide back to my presentation. Okay, so I'm back to my slides. So when a herd immunity is a condition when a state is reached so that a sufficient proportion of the population is immune, and in fact, if more imported cases are added to this, they will not induce any further secondary infection, right? And this condition can be estimated. What is the threshold required to reach herd immunity? And that threshold is also actually can be determined by R0. So in the case of COVID, if R0 is 2, when the herd immunity threshold is about half the population. Okay? And this is kind of what we're seeing in simulation as well. Right? So actually, I did not mention this explicitly, but I have set up that simulation that I just showed you to have about a 10-day recovery period. So gamma is 0.1, 1 over 10, and it has an R0 of 2, which means beta is 0.2. If gamma is 0.1, beta is 0.2, then beta of the gamma is 2. So I set it up so that the R0 is 2. Okay, so the R0 as the simulations and this fraction shows is actually also useful in determining what the threshold of herd immunity is, right? So now I asked you to look at the number of fraction of susceptible people left over. Can we try and estimate how many people at after the infection has passed through continues to be still susceptible, right? So that's something called the attack rate. The formula for the attack rate is actually given over here. If anyone is interested, we can discuss it again carefully. It turns out that the number of people getting infected, if R0 is 2, the attack rate of the population is going to be about 80%. So that means by the time the infection passes through the population, about 80% of the population will be infected. And so 1 minus 80%, about 20% of the people will continue to remain susceptible, right? So that's the final asymptotic state that you expect to see. if there were no interventions at all. So that's the naive spread of an epidemic given R0 is 2 through a population, right? So it'll be about an attack rate of 80%, herd immunity threshold of about 50%. So the next question you might ask, is it possible for communities to tailor the epidemic spread so that the population at low risk? So you realize the epidemic, is going to infect a large number of people because its R0 is relatively large. But the R, the number of people recovered, actually includes both the people who are dying, so removed, and it also includes the people who are recovered. So can we bias that fraction R in such a way that the people who were at low risk were were less protected than the people who were at high risk? So in fact, by doing this, one might imagine that you can actually protect a substantial portion of the population. So they all become recovered rather than a large fraction of them becoming, so quote unquote, removed, right? So one would therefore disproportionately try to protect older people in SARS-CoV-2 because those are that's the population that's at larger risk. So the older people above 65, especially if they have comorbidities, and those that are immune compromised are at larger risk. So you would like to disproportionately tailor your efforts towards protecting those people, right? And so, generally speaking, I think it's definitely true to say that dealing with the pandemic requires a community to become involved because of the features that I just mentioned. Now, there's another notion that I'd like to mention, which is called flattening the curve, which is something that we'll be hearing a lot. And that the theoretical basis for this is that if R0 can be decreased, and remember I said R0 by itself cannot be decreased, it's beta that you're trying to decrease, the transmission is what you're trying to decrease. What if you could decrease the R0, and the first thing that comes to mind is physical distancing, right? Then perhaps the peak, what will happen to the peak of the infection? What do you think will happen to the peak of the infection? That's a very interesting question to ask. So let me go back to the simulation and try to, sorry, I will reshare my simulation with you. So I hope you can see my simulation again. Now remember that beta in this case, my R0 in this case was 2. I'm going to turn down my beta so that the R0 is going to be 1.5. Okay, so I'm going to reduce the R0 from 2 to 1.5, presuming that some measure of control, such as physical distancing, has worked to a certain degree. How much? I don't know, but I'm just going to pick up a number and go with it. Let's see what happens. So I'm going to take my parameter beta and change it from 0.2 to 0.15. Okay, I hope you can see it in that top left corner that this number is changing. And I'm going to redo the simulations to show you what to expect, right? So here goes. There you go. So this is what you expect to see, right? Now notice in particular these curves. This was the curve for a larger R0. This is the curve for a lowered R0, right? Lowered beta, actually, right? You'll notice two features. One feature that you notice is that the peak is somewhat smaller and it is delayed. So the peak of the infection occurs further with a lower R0 and it is also lower, right? The area under the curve, the total amount of infected people, which you can find out by comparing these two, goes from about 80% in this case to about 60%. People infected is also lower somewhat. From 80% to 60% in going from beta is equal to 0.2 to beta is equal to 1.5. But the major difference here is, the more important difference over here is that the number of infections that you have at the peak, that means the number, imagine a hospital system seeing a large number of infected people appear requiring care, that number has gone down. And that is what is called flattening the curve. But notice and remember that by flattening the curve, you are prolonging the duration of the epidemic also. because it's going to now occur at a small rate over a larger period of time, in a sense. And even though you've controlled the total number of peak infections, the total number of infected people over a larger period of time is not that much smaller. Okay, so let's go back and take a look to. I'm sorry, to get this back. Let's share my screen again. Right. Right. So flattening the curve, there are certain caveats. While the infection is spread out, the total infection, the number of people infected is invariably not that much, right? The R0 control measure that is employed, whether it's lockdown, which is a severe form of control, or whether it is physical distancing with some sanitary measures and so on, the particular kind of R0 control measure employed can affect livelihoods. It makes a big difference what kind of methods you use. Some are easier to adhere to, some are harder to adhere to. There are secondary costs associated with severe measures like lockdowns and so on. And there is a trade-off between affecting livelihoods, the economy, and ultimately lives of people by locking down, right? Versus having something milder than a lockdown, which is physical distancing. And it's important to be sensitive to the numerous fallouts of these severe prolonged control measures, for the reasons that I said, for the reasons the simulation shows. Okay? It is in general a difficult thing to know what control measure will result in how much lowering of the R0. This is a hard problem, and this is something that one worries about a lot, and it's not fully clear how much can you control R0 by these different measures. That's something that one should worry about, and there's a lot of research, and one should continue to do research on this. Now let me show you one final set of simulations on 2 slides. This is something called post-intervention rebound. Let's say you lock down for a few days and then you release the lockdown, right? So this is a simulation in which so the red curve shows you what would have happened had there been no control measures exercised on the R0. The black curve says an early lockdown at 20 days. By early lockdown, I mean the moment the cases start appearing, when a few cases have appeared, you lock it down. You stay locked down for 30 days, and then you go back to a pre-lockdown condition. And you can see that during the lockdown, you had a lowered growth, but as soon as you remove the lockdown, there was the right rebound. And so you've done very little in terms of you've delayed the peak, but you've done very little in terms of flattening the curve, lowering the peak infection rate. Okay, so there's a significant rebound in this case. On the other hand, if you lock down relatively late at day 50, you lock down for the same period of time, and then you release the lockdown, you can actually not get a rebound in this, as the simulation shows, right? The peak number of cases have been reduced by about a third, and that's useful, and there is no rebound effect. So the point that these 2 slides are making is that the timing and the duration of the lockdown and your anticipation of how much you've lowered R0 during the lockdown is of great importance, right? It can make the difference. As these slides show, it can make the difference between rebound or not rebound, and so on and so forth. So I urge you to try these experiments out, and what I hope I have done is given you enough of a handle on running these simulations and creating your own simulations to try and see whether you can get insights into the sorts of things that are going on around you, and perhaps even come up with very smart ways of handling the pandemic. So as we like to say, it's a community effort. Not only does it affect everyone, but also the solutions are going to come from it. So I think I'll stop there for this part of the talk, and we will continue the second half next week. I'm sorry to have gone over time, but in the next half, when we come back in next week, I will take some data from the current SARS-CoV-2 outbreaks, and I will show you in some more detail how people go about estimating R0 based on actual data analysis. So I think I'll stop here, and I'll be happy to take questions if there are any.
Yeah, thank you, Dr. Pranay. There are a bunch of very interesting questions that I would like to that the students would like to ask you. So
Okay.
the first is a couple of students were asking that what happens to R0 when there is a chance of a relapse, and if there is a possibility of relapse in case of COVID-19.
So you, okay, I suppose you mean rebound effects. So can you ask me the question again? What do you mean if there's a chance that, are you asking about this particular epidemic, the one we are having, and whether or not we are likely to see a rebound effect?
Yeah, so the one question asks us how is the R0 affected when if the people can get a relapse in cases of diseases where there can be a relapse of a disease, then how is the R0 affected?
Yeah. Okay, so the SIR model is not tailored to a setting where a person who has previously been infected can return to the susceptible pool. There is a special kind of modeling that is done, a different kind of compartmental model called SIRS, which allows for a recovered person to become susceptible again. I presume that's what you mean when you say relapse, because that individual is now, who's recovered, is now back to the susceptible pool and can get reinfected again. Right? So one does study in the literature SIRS models, and they have somewhat different behavior than this. But essentially, you can see that the dynamics would be different. In SARS-CoV-2, one doesn't typically expect, from what's known, one doesn't really expect that a large. It's not none, but people don't typically get, so to speak, susceptible again. Okay. Does that answer it?
Yes, that was the question, I believe. Another question is asking that shouldn't the number of deaths occurring during a pandemic be also considered while tracing the trajectory of the disease? Because not considering deaths, doesn't it restore the number n to the initial population?
Okay, so yes, there are certain models that do consider deaths also. So those are the class of compartmental models which are SIRD. So you imagine that the people who've gone into the R phase, a proportion of them will die. Right? So SIRD type of models, and there's others that will account for the number of deaths. Now, the second part of the question, which says that doesn't influence the number n, because in that case you would assume the conservation law would be S plus I plus R plus D together would be n. It is about the closed. The important criteria is that the population is closed. That means there are no more births and deaths in the process, because the time scale of the epidemic is small. So essentially, one can consider models with death, but you have to do it in a different manner. And R0 by itself will not help you entirely over there, because you will also have to know what is the fraction of people that are dying. So something that is something related to the case fatality rate. So one typically, especially at the beginning of the epidemic, does not always know that. Also, different epidemics are very heterogeneous. They spread through different populations in a very different manner. Many different parts of the world will experience the epidemic differently. Even same parts of the world, two different communities will experience it differently. So all of these numbers are affected tremendously.
Okay. Yeah, that makes it clear. The next question is, what will be the impact of increased beta on herd immunity?
Okay, that's a good question. So, let me show. So, decreasing R0 by decreasing beta increases. So if R0 is lowered, say beta is lowered, then R0 will be lower. The herd immunity threshold is 1 minus 1 by R0. Okay, so you can work it out from Okay, I'll leave it as an exercise for you to work out. Herd immunity threshold is 1 minus 1 over R0, right? That's right over here, right? You can work out if R0 goes up by increasing beta versus R0 going down by decreasing beta. That number you can work out in great detail.
Okay, perfect. The next question is, how is R naught impacted when the incidence rate and mortality rate or outcomes are varying in different geographic locations?
Okay, so that it is the, I mean, the question is, if the question is difficult, the answer is even more difficult. That is exactly where professional epidemiologists spend a bulk of their time to figure things out. So the question you're asking is extraordinarily complicated. It's influenced by a lot of things and a tremendous amount of things. I think it'll take me longer than an hour to discuss the sorts of things that can influence these things. But you can imagine, I can give you a very straightforwardish answer, if somewhat hedging answer, is that the transmittivity depends on a number of things. It's a community transmission. So it depends less on an individual and it depends more on community circumstance. Okay? That's a tremendously important, that's a really important idea to keep in mind, because the environment around, not only the environment, environmental factors such as whether or not the place is hot, whether or not the place is humid, but also demographics of a place, whether or not there are young people in a country, for example, like India, that changes the behavior of the dynamics of the spread. Okay. So this is a very open-ended question, so I have to give a somewhat simple answer to it.
Sure, yeah. This was a question by a Manav team member, so I think we can have a discussion with you at
Absolutely.
some point. Another question by a student is, although they belong to the same virus family, the MERS coronavirus has very low R naught as compared to those for SARS and SARS-CoV-2. Why is it so?
Yeah, so there's a lot of speculation and it's not clear. These equations themselves will not tell you that. That's important to realize. I mean, these equations are sort of, they will look at the data in post facto, tell you what the condition is, what the situation is. So let me put it this way. Different viruses will behave differently, and you're not going to be able to know the R0 by saying what coronavirus is. Okay, what you do have to do is to actually do something at the beginning of the spread. So, for example, you might at the very beginning of the spread, if you've got very good systems in place, you might do contact tracing. You might be able to say, well, let me actually follow the people who are spreading the disease and see how many on average do they affect. So that's one way to do. The other way that I'm going to show you is, as one starts to measure the number of people, number of cases, number of people infected, and by looking at the time series of how those numbers are growing, one can actually go and fit a curve to it and produce an R0 from that, right? So it is very much a data-driven activity. The biology of the disease by itself is not going to tell you what the R0 is, because not only is it a community wide object, but also the biology tells you only so much. I mean, yes, something like measles will spread very quickly, so you have past experience with it. But with something that's novel, you really can't rely on the biology to tell you what the R0 is going to be. You actually have to measure it, and I will show that to you next.
True. So the next question is two students asking that they have heard different R naught ranges from 2 to 3.1. So they are wondering if the R naught has changed within India. And if
changed by what means?
Changed in the number. So they have heard different figures that
could R naught have been different for different parts in India or for India as a whole relative to other parts in the world? The answer is it's very likely. It's possible.
Okay.
It is possible. Yeah, and that's one of the arguments that is being given uh, across the board. I mean, yes, several scientists have suggested that the traffic networks are different in, for example, Europe versus India. Typically, one believes India is less connected than Europe. So yes, that can influence R0. But again, it's not going to be immediately clear by how much, whether you can really explain going between R0 equal to 2 to R0 equal to 3 by simply saying transport networks are denser in Europe than in India. That's a hard problem. And one really has to do a lot of work to figure it out. It is a possibility. We don't know the answer whether that is true. It's a hypothesis.
Yeah, that's very fascinating. The next question is, can we predict the severity of second wave of infection post-lockdown using this model?
So in principle, yes. But again, you have to have very good data. You have to know uh, how much you can rely on the data that you have and how much you have to extrapolate. And professional epidemiologists do this all the time. And they have, I'll give you an example. It's a complicated process. It's a complicated process because, say, case definitions might change as the epidemic is progressing, right? What you consider a death by COVID, that definition may change during the spread of an epidemic. If such a thing happens, you have to recalibrate. Uh, there might be delays in reporting. So you might one day see a large spike of cases of people who have been reported to have COVID. Now, it's unlikely that epidemiologists tell us that it's unlikely that all of those cases occurred during that day. It's just that some backlog might have been cleared somewhat late. So you have to adjust for that. So uh, during an epidemic, as it is spreading, taking care of the statistics is an exceedingly difficult task. But if you can do that, and if you have a good model, if your model does well over the data range over which you've been fitting it, then you can use, yes, to make predictions about what the lockdown. And in fact, there are papers in the literature, especially coming out from Italy, from the group of Morton Peterson, who have tried to do this. And they have good fits to the data. So yes, it's possible. In principle.
Definitely a very complex problem. The next question is, how are not is affected when considering asymptomatic COVID-19 patients? Will that cause discrepancies for or not?
Yeah, so that is a very difficult question to answer very quickly. If there are asymptomatic cases, then generally speaking, within the SIR model, you expect the disease to become endemic. That is a known result. So taking care of asymptomatic cases is hard until you actually do some serological testing and you have good numbers for those to account for in a model. You will have to augment the standard SIR model with a fraction of people who are infected but do not show symptoms. And generally speaking, one of the solutions to that problem is that the disease actually becomes endemic.
Okay, so we have time for one last question, and that is, are vaccinated individuals considered in the calculation of the R0? If yes, how would the vaccination strategies being developed globally affect the R0 value?
Yeah. So remember that when we are talking about R effective, remember it's actually on this slide, if you can see this slide, R effective is essentially R0 times S, the number of susceptible people at that given time. So if a large fraction or if a certain amount of fraction of the people have actually been immunized, then they have got antibodies and you've shrunk your susceptible pool, right? So R0, the effective, or RD or R effective, will actually be lower because the number of people who are susceptible is actually shrinking, right? So in other words, if you vaccinate a group of people, then the virus will find it harder and harder to find fresh susceptible people, right? So immunization has the effect of lowering R. Effect.
Okay, so thank you, Dr. Pranay.
Thank you.
Yeah, so many thanks, Dr. Pranay. It was a very engaging talk. And looking at the flow of questions that we got, I'm sure our participants learned a lot. I would like to thank Gayatri, Dr. Dhara, and Dr. Nagraj for organizing this webinar. And as Dr. Pranay mentioned, that we will have another webinar with us, where he will talk to us in a more hands-on manner to understanding these models. So please watch the space at Manav for the announcement, and we will see you all again next week.
Great. Thank you very much for having me, and it was a pleasure to discuss things.